So today we're going to go through the Combined Science Physics Paper 1 Foundation paper from 2022. Now we're going to go through each question in turn and go through the thought process to make sure that we can answer all the questions fully. So here we've got students investigating how the potential difference across a filament lamp affects the current in that lamp, and you've got a picture of the circuit diagram. First question, figure 2 shows a circuit symbol. Which component does that represent? Well, we've got the two cells together. Two of cells or more means that we have a battery. So it's a nice straightforward question to start you off with. 1.2, which component from figure 1 did the student use to adjust the potential difference across the lamp? Well, if we're adjusting the potential difference, that's also going to affect the current. And it's going to be this component here, which is our variable resistor. So we can, as the name suggests, we can vary the resistance just by turning the dial on the resistor, and that will adjust the potential difference. You could also draw the symbol in this case. When the voltmeter was not connected to the circuit, it gave a reading of 0.4 volts. So how could the student correct all the readings taken from the voltmeter? Well, if you've got a reading before it's connected, it's 0.4 volts too many. So you need to subtract 0.4 volts from your reading, and that will give you the correct answer on that one. Now 1.4, bit of a maths question. We've got a table of results. You need to calculate the mean current in the lamp. So what you need to do is you need to add three figures together. And I would make sure that you show your working, just in case you make a mistake, and you'll get marks for your working out. We've got three figures. You need to add the three together, then divide by 3. That gives you overall 0.55 amperes. You need to be making sure that you can use your calculator properly, just to make sure that you get the right answer from that one. And then 1.5, calculate the power of the lamp when the potential difference across the lamp was 4.8 volts. The current in the lamp was 0.5 amperes. Now the great thing about this, they give you the equation. Now I would get a highlighter pen out here and mark the fact that we've got the current. We've also got the potential difference of 4.8 volts. We need to calculate the power. So let's substitute the numbers that we've got. Well, we don't know power, so that's its P. Potential difference 4.8 multiplied by our current of 0.75 amperes. Put those numbers into your calculator and you should get the answer of 3.6 watts. Two straightforward marks, but the good marks to get. So you get the first mark for just substituting in your numbers correctly, second mark for showing the correct answer. 1.6, we need to calculate the resistance now. So again, we're given that the potential difference is 4.8 volts, the current is 0.75 amperes. Again, we're given the equation, we just need to substitute our numbers in correctly. So that means resistance R is 4.8 divided by 0.75. Again, put those numbers in your calculator and you get 6.4 ohms. And then 1.7, you need to complete the sentence. Choose the answers from the box. Each answer may be used once, more than once, or not at all. Increasing the current in a filament lamp makes the temperature of the lamp. Well, the more current you have flowing through a wire, the hotter it gets. The same is true for a filament lamp. So that is going to increase. Now, as the temperature goes up, it also means that the resistance of the lamp will go up as well. So an increase in temperature also means that we have an increase in the resistance of the lamp. So in that case, you're using the same word twice. Don't let that throw you when you answer these kind of questions. And then 1.8, you just need to be able to recognize these potential current graphs. You should be able to discount some of them. This one up here, that's your diode, so it's definitely not that one. And of course, our fixed resistor would give us second option. That means the one that we're left with is the graph showing slight kind of S curve. So that's just one of those graphs that you need to know. So that question's out at 12 marks. Hopefully you got 12 out of 12. On the second question, we've now got a question about a lift, and you've got the diagram there, and it's electric motor moves the lift is moving up. First question, as the lift moves up, how far does the counterweight move down? Well, if you look at the rope, it's all connected. So if the lift moves up, you can see that the counterweight is going to move the same distance as the lift. So we should be ticking the middle box. 2.2. What happens to the gravitational potential energy of the counterweight as it moves down? Well, if it's moving down, we're reducing its store of gravitational potential energy. So there's only one option, only one correct option, it decreases. And then 2.3, back to our maths question, calculate the change in the gravitational potential energy of the lift when it moves at 4 meters. So we've got a change in height of 4 meters, we've got a mass of 1300 kilograms, and in these kind of questions they generally always give you the gravitational field strength. We've got 3 numbers to use, and we just need to substitute them into our equation. So we've got this one, energy, EP, equals mass, 1300, multiplied by 9.8, gravitational field strength, multiplied by 4, our change in height. You picked up your first mark already, put those numbers in your calculator, and you end up with the answer of 50,960 joules. And that's the second mark for calculating the answer correctly. Now, 2.4. We've got some options of some words. Again, we're not going to use all the words, and in this case we need you to complete the sentence. So friction between the cables, between the brakes and the cable, causes the speed of the lift to decrease. As the speed decreases, there's a decrease in what store of energy? Well, if we're going slower, that's all to do, movement is all to do with our kinetic store of energy. So that's very much kinetic. As the speed increases, there's an increase in what store of energy of the brakes. Now you might be thinking this is going to be thermal store of energy, and sometimes rather than using thermal, they might use internal, and that's the word we need to use in this particular case. So it's the actual energy within the actual particles, which is linked to the thermal store. 2.5. We've got a tick box exercise here. So the motor transfers different amounts of energy each time people use the lift. What factors are going to affect the amount of energy transferred by the motor as the lift moves? So if you think about it, this is all to do with how much effort, how much work is being done. So the further the lift moves, well, that seems rather sensible that that's going to affect the amount of energy being transferred. Things like the height of the building, the length of the steel cable, that's nothing to do with the lift really. The maximum power of the motor, that doesn't really affect things. Power is all to do with the rate at which energy is transferred, and we're not really looking at the time. So we can discount those 3 answers, and then of course the more people in the lift, the more weight there is, the more work that has to be done by the lift, so it takes more energy. So you're looking at the first and the last options there. You're going to mark for each correct answer. And then moving on to 2.6, again you've got a calculation to carry out. So we've got a stretch of the cable by 0.015 meters. We're being told that the cable acts like a spring, and we're given the spring constant of 880,000. We've got to calculate the elastic potential energy of the stretched cable. So the stretch means that that's the extension of the actual cable. But we've got our 2 numbers that we need to substitute into our formula. And we've got elastic potential energy, EE, equals 0.5 multiplied by our spring constant, so 880,000, and then we're multiplying it by the extension squared. Now in the past, this part of the calculation has thrown people squaring our extension, squaring 0.015. Put all those numbers into your calculator carefully and you will end up with 99 joules. If you're going to go wrong in this calculation, it'll be something to do with the squaring part of it. And then the final part to this question, a lift system using a counterweight is more efficient than a lift system that doesn't use a counterweight. So how does having a more efficient system affect the energy transferred by the motor? If we are being more efficient, we are using the energy available better. So it actually means that we have to transfer less energy to get the same effect. Now that question is out of 11 marks, so again, hopefully you've got 11 out of 11. Question 3. So a teacher demonstrated that the radioactive isotope americium-241 emits alpha particles. We've got the equipment used there. Now, we've been told that our nucleus emits an alpha particle and turns into a Neptunium nucleus. So we need to work out which is the correct nuclear equation for this decay. Now, this might throw people because you might be looking for the alpha sign for an alpha particle, which we often write like that. Sometimes the exam board will write it as it's done in this question, showing it as being helium-4 Remember, this is just the equivalent of a helium nucleus, not a helium atom. Now, here, if we're losing 2 protons and 2 neutrons from our nucleus, we need to take 2 off the bottom number, off the 95. So we need to be looking for either the options, which gives us 93. So we've got those 2 possibilities. Now, we're losing 4 off the mass, so we need to take 4 from the 241, and that should give us 237. So it means that the top, the first option, is the correct option to go for. 3.2. What is the furthest distance that alpha radiation can travel in air? If you remember, it's got the least penetration, certainly through the air. It's a few centimetres, and that's the option we need to go for. 3.3. The teacher placed a piece of paper between the radioactive sample and the radiation detector. The reading on the count rate meter decreased by a large amount. What does that tell us about the alpha radiation? Well, it tells us that paper is good for stopping alpha radiation. That's the only conclusion we can make from that bit of information. Now with 3.4, we're now using a source of beta radiation. Which symbol represents a beta particle? Now again, you might be used to showing a beta particle as that. It is a high-speed electron, so sometimes, as I've done in this case, they use E to represent the beta particle. Now the charge is -1, remember it's an electron, and electrons generally have no mass. So we have our top box is the only correct option in this case. And then 3.5. The count rate from the source was 119 plus or minus 7 counts per second. Calculate the smallest count rate this could have been. Well, that plus or minus 7 just shows you the variation. It shows the range that to work out the highest count rate, it would be 119 plus 7. To calculate the smallest count rate, and this is what we need to do, it's 119 minus 7. You might not even need your calculator to work that one out, and it comes out as 112 counts per second. 3.6. Draw one line from each type of variable to the description. So you've got your control variable, you've got your dependent variable, you've got your independent variable. Now, the independent variable is the thing that you're changing. And in this investigation, it was the distance between the source and the detector. The dependent variable is what do we measure as a result of that change. Well, we measured the count rate. In terms of control variables, well, they're the things we keep the same. We have to keep using the same radioactive source. And there's your 3 marks. It's important you remember your variables for all your science papers. And the final question, or the final part of this question, we've got our radioactive source, and we're monitoring the count rate per second as we move the actual detector away from the radioactive source. We've got to describe the relationship between the distance from the source and the count rate. Now this is worth 2 marks. Now the first mark is to make the point that as the distance increases, the count rate decreases. So hopefully you can see that clearly from the graph. Now to get the second mark, you need to look at this part. Where does the graph go to 0? Where do our count rate go to 0? And that's as the distance increases, the count rate decreases until, and it's about 42 centimeters if you look at your graph carefully, until 42 centimeters, where the count rate, the rate equals 0. And that's where you get your second mark from. That total question was out of 10. Hopefully you got 10 out of 10. Well done. Question number 4. Alright, so we've now got a swimmer wearing a wetsuit. The wetsuit helps keeps the swimmers warm. Now, the student wrapped a thermometer in a piece of wetsuit material and placed the thermometer in water containing ice. So you've got a diagram of the setup there. So after 30 seconds in the water, the temperature of the thermometer had decreased by 7.5 degrees centigrade. You need to calculate the average decrease in temperature each second. Now, again, get your highlighter pen out, marker pen out, pencil, whatever. We've got time of 30 seconds. We've got a temperature decrease of 7.5 degrees centigrade. What is the average decrease in temperature per second? So we need to be dividing by time here. So our decrease in temperature, so T equals, in this case it's going to be 7.5 divided by 30. Put that number in your calculator and you get 0.25 degrees centigrade. Generally where people go wrong in this question is they think that they have to get some kind of whole number. So they divide, or a bigger number, so they divide 30 by 7.5. If you got 4 degrees, that's clearly wrong, because that's time per degree centigrade. You have to calculate it the other way around. So don't be too worried if the number looks quite small, it's absolutely fine. Now, this one we've got different materials being tested, and all the materials were the same thickness, and what we've got here is the starting temperature was 21 degrees centigrade, and then we've got the results in the table with the 4 different materials. Now, you've got a bar chart to fill in here. You should be looking at this as the easiest 2 marks that you're going to pick up in your exam. Now, the first thing you need to do is label the y-axis. Now, if you look at the table, well, if you look at the x-axis, which is material, there's a material in the table. When you have to label any of the axes, just use the labels that they use in the table. So here we've got temperature in degrees C. You have to include the unit there to get the mark. So there's our first mark. And then all we've got to do here is plot the graph correctly. So for y, we're going up to 16. So you're going to use a ruler to do this, and that would, well, it wouldn't get you the mark, you have to do both correctly, and then the second bar would go to 12 for Z. You don't need to waste time on colouring this in or shading this in, just make sure it's in the right place. You need to be precise. If you're over half a square out, you don't get the marks for it, but you should be looking at that as being 2 relatively easy marks to get. Now, which material is the best thermal insulator? And you have to give a reason for your answer. Well, in this case, Y is the best thermal insulator because it showed the smallest change in temperature. So it's important you're correct with this, so showed the smallest change in temperature. This is where you need to look at your data carefully. You don't really want to be looking for the biggest number, you want to be looking for, in this case, we're trying to keep the temperature as high as possible, so we want the smallest loss of heat, therefore we want the smallest change in temperature. And then 4.4, the student tested a new material with a greater thermal conductivity than the material Z. The piece of new material with the same size and thickness as material Z. What was the temperature of the thermometer after 30 seconds? Well, in this case, it's got greater thermal conductivity, so it's going to be very good at, or it's going to be better at losing heat. So our correct answer here is less than 12 degrees centigrade. And then 4.5, still part of this question. During the investigation, 0.015 kilograms of the ice melted. The temperature of the water and the ice did not change. So we should be thinking about change of state at this point. We've got the latent heat of fusion of ice. Again, that's our change of state. We need to calculate the energy needed to melt the ice. It even gives us the equation to use. And we just need to substitute our numbers in. So we've got the energy to melt the ice, that's just E. We've got a mass of 0.015 kilograms, and we just multiply that by the specific latent heat, which we're given as 334,000 joules per kilogram. You put those numbers into your calculator, and you'll come out with the answer of 5,010 joules. This question is probably tricky, just to make sure that you use your calculator properly, you put your numbers in correctly, especially with 334,000 and also with your decimal place on the mass. But you should look at that as being fairly easy marks. Now we've got some data and we're trying to work out the density. So you've got the table of results there. 4.6 is completing the sentence. Choose the answer from the box. The results show that compared to the ruler, the micrometer has a higher watt. Well, if you look at the micrometer, we're going to 3 decimal places compared with just 1 decimal place with the ruler. It might make it more precise. The calibration isn't part of it. Reproducibility, nothing to do with that. Resolution is, in a way, the smallest measurement, which means that we can go down to a smaller measurement with the micrometer, so our correct answer here would be resolution. And then use the physics equation sheet. This is an easy mark. It's linking density, mass and volume. So you've got density equals mass over volume. I've written it as symbols, which is acceptable. You can write it out as words. It's up to you, as long as you're using the correct symbols and obviously the correct words. An easy mark. But then we need to use that formula to calculate this next question. So we've got density is mass over volume. Now we don't get a mark for writing that formula out again. We've got that in the previous question. But we do get a mark for substituting in the numbers that we've got. So here we're being told that the density is 0.300. Now we need to calculate the mass. So the mass is our unknown one, but we've been given the volume of 0.186. You get a mark for substituting in the numbers correctly. Now the second mark comes from rearranging it to get m, making m the subject of the formula. So we have m equals 0.300. Of course, we need to multiply both sides by 0.186 to get m by itself. We then just need to plug those numbers into your calculator, and it's going to be a small decimal number, but don't worry about that. you should end up with 0.0558 grams. In this case, it's not asking you to do any rounding down, so I would just leave that number as what comes up on your calculator. Now that question is out of 14 marks. Hopefully you got 14 out of 14. Alright, question 5.1. We've got a whole load of data here which shows the energy resources used to meet the demands for electrical power in the UK just for one day in 2020. The question is asking the maximum demand for electrical power on that day was at 6 p.m. Determine the percentage of the maximum demand for electrical power that was generated using gas. Now this is worth 3 marks, and in this case we need to be using the graph. So we need to find 6 o'clock on the graph, which is here, and if we draw that line up, and obviously you can do this much more accurately with a ruler, and we've got the total demand, which at 6 p.m. Would be a nice round number of 30,000 gigawatts. So the demand, the total demand equals 30,000 gigawatts. Now we need to look at gas, that's what we're interested in. If we go up and then go across, and again, this is where you need to be using your ruler. And you should see that this comes out as being 16,500 gigawatts. So 16,500. Now, you get a mark just for picking up those numbers off the graph. So it's important that you do that properly. And then, we've got to see what percentage of our electricity comes from gas. So we put the gas number at the top, 16,500. We divide that by 30,000, the total energy. We want to make it a percentage, so we need to multiply that by 100. If you put those numbers into your calculator, you'll come up with a correct answer of 55%. So there's quite a lot of work in there to get the 3 marks, because you need to be using the graph, and then you need to do the calculation. But if you get comfortable with it, it's 3 nice, easy marks. Now the UK government wants to reduce carbon emissions as much as possible. Which energy resources need to be used less to achieve this? Now you need to look through the list, and you can get rid of some very quickly. Well, things like wind doesn't produce any CO2, neither does nuclear. So you can get rid of that one. Now wind and coal, one is still producing carbon, but one isn't. And again, the gas and nuclear, one produces CO2, that's gas, but nuclear doesn't. So it means that we've got coal and gas left over. There are 2 fossil fuels, so it's very much those 2. Alright, network of transformers and transmission cables transfers electrical power from power stations to consumers. What is this network called? This is just something you've got to remember. We call it the national grid. 5.4. Explain how using step-up transformers make the network efficient. Now, a step-up transformer increases the potential difference. At the same time, if the potential difference goes up, it means that the current goes down. So it decreases current. The whole reason for decreasing the current is that if you have a high current travelling through the cables, they will heat up a lot, and we get lots of unnecessary, unwanted energy transfers and we lose a lot of thermal store of energy. So by decreasing the current, there's going to be less energy used to kind of heat up the cables, less energy is being lost to the surroundings. So your 3rd mark, therefore, less energy is lost to the surroundings. Or you could talk about less energy is lost to heating the cables. Either of those 2 options will get you the 3rd mark. So you need your 1st mark for talking about increasing the potential difference, 2nd mark for decreasing the current, and then your third mark, it means that less energy is lost. Right, and then question 6. This is our 6-mark question, and you should be looking at being able to get pretty much all the marks on this one. Now, this is where you need to read the question carefully, because the student made measurements to determine the specific heat capacity of vegetable oil. You've shown the equipment used. Now, you need to write a method here, but you also need to explain how to use the actual equipment. So it's not good enough to say take the temperature. You need to be talking about taking the temperature with the thermometer. Measure the mass of the oil. You need to measure the mass of the oil with top pan balance to get all the marks possible. So on this, the first part of this method, it would be to use the top pan balance to measure the mass of oil. I'm hoping you write this a lot more neater than I do. And that oil, the oil is placed in the beaker. We then need to record the temperature of the oil using a thermometer. We then need to place the oil, or place the beaker of oil, on the heater and turn the heater on. We need to make the point that the heater is connected to the joule meter, and the joule meter will measure how much energy is transferred to the oil. And then we'll leave that for a while. So once the temperature of the oil has increased by, in this case we're going to do it by 10 degrees centigrade, by 10 degrees C, we need to stop heating and record the energy. Again, I'm just using some abbreviations. The energy transferred on a joule meter. So here we're explaining exactly how we're using each bit of the equipment and what readings we're taking. And it's important to be talking about recording these numbers. We then, just going to move on to the other side of the page here, put the values into the formula. Remember, we need to be explaining how to calculate the specific heat capacity, so use a data sheet to get the correct formula. So it's the energy transfer is mass multiplied by the specific heat capacity multiplied by the change in temperature, and we do that to calculate the specific heat capacity. That's just C. Now, a nice bit to add on as well, just to get hopefully guarantee that we get the full 6 marks. Repeat this twice, so we end up with 3 results. Repeat this twice more to calculate a mean. If you include that, you've got 6 marks. The important thing here is making sure that you're explaining how to use each bit of equipment. So, you know, in some cases, you could almost write on above here, thermometer to take temperature, beaker to hold oil, electric heater to heat oil, joule meter to record the amount of energy transferred, top band balance, measure mass. Now, if you make notes up here, you will still get credit for it. Don't worry about writing this out in full sentences. I would suggest you bullet point methods. It makes it much easier for your examiner to mark. Alright, so 6.2, we need to give one risk when using the equipment in figure 10. The risk are, well, the best one to go for is burns or scalds. So remember here we're talking about the actual risk, not the hazard. So we're not talking about hot oil, which would be the hazard. It's the risk, what could potentially happen to it. And burning or getting scalded is the most likely thing. Now, a different student did not have a joule meter and calculated the energy transferred by the electric heater. Saying here, use the physics equations sheet to answer questions 6.3 and 6.4. We've got to write down the equation linking energy transferred, power and time. Well, that is just looking at the formula sheet. Power is energy transferred over time. Nice straightforward kind of mark. And then the next question, we're going to have to use that formula. So we've got power equals energy over time. Remember, we don't get the mark for writing that out again, but we do get a mark for transferring in the numbers we've got. So we've got a power number here. We've got a transfer of that number of joules of energy. We've got to work out the time. So we've got power is 50 equals 4,750. A bit clearer, over t, which is our unknown. We now get our first mark from that. We then start trying to solve our equation, so we end up with t equals 4,750 divided by 50. We've now got 2 marks. We then put those numbers in our calculator and you should get the correct answer of 95 seconds. There's your third mark. Well done. Now, here we've got a question about deep fryer. So the vegetable oil is heated by an electric heating element and the food is then cooked in the hot vegetable oil. The deep fryer contains electrical components to monitor the temperature of the vegetable oil. Here we've got a graph showing the resistance of the electrical components, how it changes with temperature. Right, so we should be thinking, right, back to our electricity topic, what component changes with temperature? Well, changes its resistance. So it's some type of resistor. It's our thermistor. So there's our mark from that. And then 6.6, our electric heating element in the deep fryer automatically switches off when the vegetable oil reaches a certain temperature. Graph figure 12 shows us the temperature of the vegetable oil changed after the deep fryer was switched on. We need to determine the resistance of the electrical component when the electric heating element is automatically switched off. Now, if we look at the temperature of the oil, where it goes flat is clearly where our fryer turns itself off. If you look carefully at the axes, you've got a temperature of 160 degrees centigrade. So that's the temperature when the oil will, that the machine turns off. Now we need to take that temperature and use that with figure 11. So we need to find out 160 degrees on this scale, which comes in about here. We need to draw that up to the line, and then we just need to draw across. So again, you're going to have a nice straight line because you're going to use a ruler, and then you just need to read off the scale. Make sure you read off correctly, and this comes out as being 240. So although they're giving you plenty of lines to write on, in a way the examiner actually looks at the graph, would have looked at both graphs to see where you get the marks from. So if you just wrote your resistance as being 240 ohms, you've got the mark. If you made a note of the 160 degrees centigrade but you didn't get the correct resistance number. You could still pick up a mark just for that. But this is quite a lot of work really for 2 marks, because you have to read off 2 different graphs. Well done if you got both marks. And then 6.7, last question. Some chips were put in the deep fryer. In the deep fryer, water in the chips underwent a physical change and became steam. Why is this classed as a physical change? Right, so we now need to have a look for our best answer. All water can change to steam. Yeah, that's true, but it doesn't actually answer our question here. No chemicals are involved when water changes to steam. Well, technically water is a chemical, so we can probably get rid of that one as well. The change from water to steam can be detected visually. That's true, but it doesn't really explain why this is a physical change. You can see, you can have physical changes that we can't actually see. The water will recover its original properties if the steam is cooled. Now, that's a very wordy way of saying that if we cool the steam, it returns back to water. That is our physical change. So it's the final box. That final question is out of 15. Hopefully you got 15 out of 15. Well done, you're now at the end of the paper, so you can tot up your score out of a maximum of 70.